Hello everyone. Welcome to this video presentation of our CVPR paper entitled SpiderGANs, Leveraging Friendly Neighbors to Accelerate GAN Training. My name is Siddharth Ashokan and I am from the Robert Bosch Center for Cyber-Physical Systems at the Indian Institute of Science, Bangalore, India. My co-author on this paper is Chandrasekhar Sirumantula, also from IISc. Before we dive into the details, let's take a look at the overview of the proposed work. The core idea behind SpiderGANs is to replace Gaussian or other parametric choices of input with samples coming from closely related datasets. To identify these friendly neighborhood inputs, we proposed a site inception distance or SID, which can measure both distances and relative diversity between datasets. We employ SID to identify friendly neighbors of a target and show that SpiderGANs trained with such inputs leverage underlying structural similarity to accelerate training. SpiderGANs can achieve state-of-the-art FID in merely a fifth of the training time compared to the baseline GANs. With an overview of the proposed approach complete, let's now dive into the results of the paper in detail. Before delving into the specifics, consider a brief introduction to Generative Adversarial Networks or GANs, a generative modeling framework that's gained a lot of popularity over the past decade. GANs comprise a pair of neural networks originally envisioned for the task of transforming noise to images. Since then, the quality of images generated by GANs have drastically improved. As an example, we consider images drawn from the MetFaces dataset here. The dataset samples can be seen as coming from an underlying distribution PD. A min-max game ensues between the generator and the discriminator to learn the data distribution. The generator network accepts high-dimensional noise as input, typically Gaussian or uniform distributed, and learns to transform it to the target samples following a distribution PG. The discriminator network in most common settings is a two-class classifier tasked with differentiating between the real and the fake samples. This information is percolated back to the generator through appropriately defined loss functions. The generator is trained to minimize the chosen loss by creating samples that are continually harder to classify by the discriminator. The objective is to learn the optimal generator, one that creates samples that are indistinguishable from the reals, ultimately confusing the discriminator. Considering the standard GAN formulation, we specifically focus on the generator and in particular the Gaussian or uniform distributed parametric inputs provided to it. Fundamentally, the generator can be seen as learning a mapping from the Gaussian to a high-dimensional manifold corresponding to the dataset considered, which in this case is MetFaces. However, the Gaussian in n dimensions, unlike in 2D, does not lend itself easily to image feature space interpolation, as this can be shown to lie in a soap bubble-like manifold in high-dimensional spaces. Existing approaches address this issue of interpolation by replacing the Gaussian prior with choices such as the gamma, Cauchy, Gaussian mixture, or other non-parametric distributions. Along yet another vertical, image-to-image translation GANs tackle the issue of training GANs with images as input. In this context, the generated images typically maintain some form of semantic, pairwise, or feature-level consistency between the source and the target. Examples include image style transfer, in-painting, and domain adaptation applications, just to name a few. In this paper, we take a generalized approach to image-to-image translation GANs, wherein we replace the standard parametric noise input to the generator with samples drawn from closely related datasets. We will demonstrate that a good choice for a closely related dataset improves the GAN performance. However, it remains to be shown how we should go about identifying these friendly neighborhood datasets. Our motivation in finding friendly neighbors is based on the interpretation of the manifold hypothesis that the various datasets, either visually similar or otherwise, lie close to one another in some high-dimensional space, creating the so-called neighborhood of a target. In this case, the target at the center of the web is MetFaces, and the potential neighbors such as Celebi, Ukiyo-e faces, MNIST, SVHN, CIFAR10, or ImageNet are all depicted around it. Furthermore, these neighborhoods need not be symmetric. For example, assuming another scenario where SVHN is the target, it is entirely possible for SVHN to be closer as an input to MetFaces as the target than it would be for the case when MetFaces is the input and SVHN is the target. To quantify these distances between sources and target datasets, we leverage the kernel-based poly-LSGAN discriminator, which involves a polyharmonic spline interpolator defined over the source and target samples. In particular, we observe that given the discriminator function dp star and a test sample x drawn from the target, the function is 0 when the source and targets coincide, as seen in the case of A. The function is positive when the source is far away from the target, as seen in B, and the function is negative when the source has mode collapsed into the target, as seen in C. The scenario for mode collapse also represents a scenario where the source would have less diversity in samples compared to the target. Based on this formulation, we define the sign distance as the average value of the discriminator function computed over multiple such test samples x drawn from a cubic region C centered around the target, depicted here as a green square. When plotting the sign distance as a function of the cube length r, We see behavior that mimics the potential functions, where the discriminator is effectively measuring the charge density inside the cube C, with the target mimicking negative charges and the source being positive charges. Similar curves can be drawn for scenarios where the source has converged to or has mode collapsed into the subspace of the target. To compute the signed distance over images, we consider the approach advocated for in FID and KID metrics and compute the distance over inception embeddings of the images, giving rise to the signed inception distance or SID. The SpiderGAN approach can then be seen as identifying friendly neighbors of a target based on SID and training the generator with inputs drawn from these friendly neighborhood datasets. The table here summarizes the area under the SID curve for various pairs of source and target datasets considered. As an example, considering MNIST, we observe that the performance of the GAN significantly improved when training with friendly neighbor inputs, both in terms of FID convergence rates and the converged FID score itself. SpiderGANs are able to discover structural similarity between the input and output stages. In the case of the trousers in fashion MNIST mapping to the digit class 1, this correlates with visual similarity, while in the case of the airplane class in CIFAR 10 clustering to the male ukiyo-e faces, the structural similarity is implicit. A major advantage of SpiderGANs is the novel transfer learning framework we propose in terms of cascading SpiderGANs. Given any pre-trained GAN whose output distribution is a friendly neighbor of a target, the output of that stage 1 pre-trained GAN can be used as the input to a stage 2 SpiderGAN. Essentially, no pre-trained GAN gets left behind and can serve to accelerate training brand new GANs. We showed that training cascading SpiderGANs with stage 1 style GANs pre-trained on tiny ImageNet inputs results in state-of-the-art performance on the stage 2 Spider style GAN on FFHQ, AFHQ, CATs, MET faces, and ukiyo-e faces datasets, all in a fifth of the training time. Furthermore, cascading GANs allows us to perform interpolations on both the first and second stage inputs. The experimental validation showed that interpolations in stage 1 lead to diverse but coarse transitions in the output, while interpolations in stage 2 lead to finer transitions, which gives us flexibility in controlling the features we wish to change. This is demonstrated by the animation we have here. Bear in mind that both rows of images are the output of the same two-stage cascaded GAN, but with interpolations being performed at different input stages. To summarize, in our paper, we developed a novel framework to training GANs with friendly neighbor inputs. We derived the signed inception distance or SID based on the polyharmonic kernel discriminator function to identify such friendly neighbors. Training SpiderGANs resulted in state-of-the-art performance in a fraction of the training time. The source code for implementing Spider style GANs and the SID measure can be accessed by scanning the QR codes shown here. These are the key references cited across this talk. And with that, I'd like to thank you all for your attention and conclude my talk.